So, you're sitting in a metal tube, 35,000 feet in the air, cruising at over 500 miles per hour, and maybe you're watching a movie or, complaining about the snack selection. But have you ever stopped to think about how absolutely insane that is? How does this massive multi-ton machine just hang out in the sky? It feels like magic, but it's actually something even cooler. A perfect symphony of physics, engineering, and some seriously advanced technology. And today, we're going to pull back the curtain on this everyday miracle. My name is Garala, and like you, I've always been fascinated by the big questions. And how do planes fly? Is one of the biggest. It's not just one simple answer. It's a whole collection of brilliant ideas working together. From the fundamental forces that battle it out every second of a flight, to the mind-bogglingly complex systems that keep everything running smoothly, it's a story of human ingenuity. So buckle up, because in this video, we're going on a deep dive. We're going to break down everything from the basic principles that get a plane off the ground to the futuristic innovations that are changing the way we fly. We'll look at the engines, the controls, the secret safety systems, and by the end, you'll look at the next plane you see in the sky, not as a simple object, but as the incredible feat of engineering it truly is. Let's get started. Okay, so to understand how an airplane flies, you first need to understand that it's in a constant, high-stakes tug-of-war with the universe. Seriously, there are 4 fundamental forces acting on it at all times, and the entire science of flight is about managing this battle. First up, we have weight. This one's pretty simple. It's the force of gravity pulling the airplane and everything in it, you, your luggage, the questionable airplane food, down towards the center of the Earth. It's the relentless force that wants the plane on the ground. Opposing weight is the superstar of the show lift. Lift is the upward force that's generated primarily by the wings, and it's the force that says, nope, we're going up. For an airplane to climb, or even just stay at a constant altitude, the force of lift has to be greater than or equal to the force of weight. If weight wins, the plane goes down. If lift wins, the plane goes up. It's this beautiful, delicate balance that makes flight possible. And we'll get into exactly how wings perform this magic trick in a bit. Now let's talk about moving forward. That's where thrust comes in. Thrust is the pushing or pulling force generated by the engines. Whether it's a propeller spinning or a jet engine blasting out hot gas, thrust is what propels the airplane through the air. It's the go button. Without thrust, the plane is just a very, very heavy glider. This force is all about overcoming the resistance of the air and getting the plane moving fast enough for the wings to do their job. And the force that's always trying to hold the plane back, the arch nemesis of thrust, is drag. Drag is the force of air resistance. Think about sticking your hand out of a moving car window. That force pushing your hand back is drag. The airplane's entire body is constantly fighting against this friction from the air molecules it's plowing through. Engineers spend countless hours designing planes to be as sleek and aerodynamic as possible, precisely to minimize this pesky drag force. So you have these 4 forces in a constant dance. When you're cruising at a steady speed and altitude, they're all in perfect balance. Lift equals weight, and thrust equals drag. The plane is in a state of equilibrium, just sailing smoothly through the sky. Any change to one of these forces will cause a change in the plane's flight path. Want to climb? Increase thrust, which increases speed, which in turn increases lift. It's that simple and that complex. Understanding this 4-way tug-of-war is the absolute foundation of aeronautics. Every maneuver a pilot makes, from takeoff to landing, is about intentionally unbalancing and then rebalancing these 4 forces. It's not just about overpowering gravity. It's about mastering this intricate relationship between lift, weight, thrust, and drag. And the key to unlocking that mastery starts with the wing. So, we know lift is the hero force that defies gravity, but how is it actually created? It's not magic, it's physics, and it has a lot to do with the special shape of an airplane's wing, called an airfoil. If you look at a wing from the side, you'll notice it's curved on top and flatter on the bottom. This specific shape is the secret sauce. It's designed to manipulate the air that flows over and under it in a very clever way, and that's where a brilliant 18th century Swiss mathematician named Daniel Bernoulli comes into the picture. Bernoulli figured out something incredible about fluids, and remember, air is a fluid. His principle states that as the speed of a fluid increases, its pressure decreases. This is the key. Because of the curved top surface of the wing, the air that travels over the top has a longer path to travel than the air that goes straight across the flatter bottom surface. To meet up at the back edge of the wing at the same time, the air on top has to speed up. It's like two runners on a track with different length lanes. The one on the outside has to run faster. And according to Bernoulli's principle, what happens when that air on top speeds up? Its pressure drops. So now you have a situation where you have higher pressure air pushing up on the bottom of the wing and lower pressure air on the top of the wing. This pressure difference creates a net upward force. That force is lift. It's literally the wing being pushed and sucked upwards by the air itself. It's a beautifully elegant piece of physics in action every time a plane takes off. Now there's another factor at play here, which is Newton's third law of motion. For every action, there's an equal and opposite reaction. The bottom of the wing is also slightly angled, which physically deflects air downwards. As the wing pushes the air down, the action, the air pushes the wing up, the reaction. So you have this combination of the Bernoulli effect creating a pressure differential and the wing physically pushing air down. Together, they create the powerful force of lift. There's even a formula for this. The lift formula looks something like L equals 1/2 times D times V squared times S times CL. Whoa, science, let's break it down. L is the lift. D is the air density. Thinner air at high altitudes means less lift. V is the velocity or speed squared. This is huge. It means doubling your speed quadruples your lift. S is the surface area of the wing. Bigger wings mean more lift. And CL is the coefficient of lift, a number that accounts for the wing's shape, the airfoil, and its angle of attack, the angle at which it meets the oncoming air. So pilots and airplane systems are constantly managing these variables. To take off, they need to get the velocity, V, high enough to generate enough lift to overcome the plane's weight. They can also increase the angle of attack or extend flaps and slats on the wings, which effectively changes the wing's shape and surface area, S and CL, to generate even more lift at lower speeds. It's a dynamic process, all based on this fundamental principle of pressure and motion. Now that we've got the forces down, let's take a look at the actual machine. Think of an airplane like a body. It has different parts that all have a very specific job to do to make the whole thing work. The main body part, the big tube you sit in, is called the fuselage. Its primary job is to hold everything together, the passengers, the cargo, the crew, and to connect the wings and tail. It's the central structure that everything else is attached to. Then you have the wings, which we already know are the lift-generating superstars. But they do more than just that. The wings are also where most of the fuel is stored. Storing fuel in the wings is incredibly efficient. It uses available space, and the weight of the fuel actually helps to counteract the bending forces that lift puts on the wing roots during flight, reducing structural stress. It's a brilliant piece of integrated design that solves multiple problems at once. Attached to the wings, or sometimes the fuselage, are the engines. These are the powerhouses. As we discussed, their job is to produce the thrust needed to push the airplane forward through the air, overcoming drag, and allowing the wings to generate lift. We'll do a whole deep dive into how jet engines work in a minute, but for now, just know they are the muscle of the aircraft, providing the raw power needed for flight. At the very front of the fuselage is the cockpit, or flight deck. This is the brain of the airplane. It's where the pilots sit, surrounded by a dizzying array of screens, controls, and instruments that allow them to fly the plane, navigate, communicate with air traffic control, and monitor every single system on the aircraft. It's the command center where all the human decisions are made to guide this complex machine through the sky. At the back, you have the tail assembly, also called the empennage. This is crucial for stability and control. It typically consists of a vertical stabilizer, the fin that sticks up, and a horizontal stabilizer. These act like the feathers on an arrow, keeping the plane flying straight and level. Mounted on the back of these stabilizers are control surfaces that the pilot uses to steer the plane, which we'll get to in detail later. Finally, you have the parts that are only really used at the beginning and end of the flight, the landing gear. The wheels, tires, and struts are designed to do two things: allow the plane to taxi around on the ground and, more importantly, absorb the massive energy of landing. Modern landing gear is an engineering marvel, capable of handling immense forces and bringing a multi-ton aircraft to a safe stop. Together, these components form the complete anatomy of a modern airliner. Jet engines look incredibly complex from the outside, but honestly, their operation can be broken down into a beautifully simple four-part cycle. I like to call it the suck, squeeze, bang, blow principle. So, it all starts with the first step, intake or suck. At the front of the engine is a giant fan with massive blades. This fan sucks in a huge amount of air from the atmosphere. In a large modern engine like the one on a 777, it can suck in the volume of air in a squash court every single second. Once the air is inside, it moves to the next stage: compression or squeeze. The air is funneled into a section with a series of smaller and smaller spinning blades called compressors. Each stage of the compressor squeezes the air, packing the molecules closer and closer together. This process dramatically increases the pressure and temperature of the air. By the time it leaves the compressor section, the air is incredibly hot and dense, packed with potential energy. Now for the fun part: combustion or bang. This highly compressed hot air is sprayed with a fine mist of jet fuel and ignited. This creates a controlled, continuous explosion. It's not like the explosion in a car engine that happens in distinct pops. It's a constant, roaring fire. This combustion releases a massive amount of energy, causing the gases to expand violently and heat up to temperatures over 2000 degrees Celsius. These super hot, high-energy gases need to go somewhere, and that leads to the final stage: exhaust or blow. These expanding hot gases rush out the back of the engine, but on their way out, they have one more job to do. They pass through another set of blades called the turbine. The turbine is connected by a shaft all the way back to the compressor and the big fan at the front. The rushing exhaust gases spin the turbine, and the turbine's job is to power the compressor and the fan, keeping the whole cycle going. It's a self-sustaining process. This whole operation is a perfect example of Newton's third law of motion. The action is the engine blasting this huge mass of hot gas out the back at incredible speed. The equal and opposite reaction is the engine, and therefore the airplane it's attached to, being pushed forward with immense force. That forward push is thrust. It's so powerful and elegant. Interestingly, in modern high-bypass turbofan engines, the big fan at the front actually pushes a lot of the air it sucks in around the core of the engine. This bypassed air doesn't go through the combustion process, but is just accelerated out the back. This cooler, slower-moving air mixes with the hot, fast-moving exhaust from the core, making the engine significantly quieter and much more fuel-efficient. It's a brilliant design that powers nearly all modern airliners. Okay, so the plane is in the air, but how does a pilot actually steer it? You can't just turn a wheel like in a car. Instead, pilots use a system of movable surfaces on the wings and tail to control how the plane moves through the air. An airplane can move on 3 axes: pitch, yaw, and roll. Mastering flight means mastering the control of these 3 movements. Let's start with pitch. Pitch is the up and down movement of the airplane's nose. This is controlled by the elevators, which are small, hinged flaps on the back of the horizontal stabilizer on the tail. When the pilot pulls back on the control column, the elevators deflect upwards. This pushes the tail down, which causes the nose of the plane to pitch up. Pushing the control column forward does the opposite. The elevators go down, the tail goes up, and the nose pitches down. This is how a pilot makes the plane climb or descend. Next up is yaw, which is the side-to-side movement of the nose, like shaking your head no. Yaw is controlled by the rudder, which is the hinged section on the back of the vertical stabilizer, the big fin on the tail. The pilot controls the rudder with their feet using rudder pedals. Pushing the left pedal moves the rudder to the left, which pushes the tail to the right and makes the nose yaw to the left. Pushing the right pedal does the opposite. The rudder is essential for making coordinated turns and for keeping the plane straight during takeoff and landing, especially in a crosswind. The third and perhaps most dynamic movement is roll. Roll is the rotation of the airplane around its fuselage, like a corkscrew motion, where one wing goes up and the other goes down. This is controlled by ailerons, which are hinged flaps on the trailing edge of the wings, way out near the tips. When the pilot moves the control stick or yoke to the left aileron goes up, decreasing lift on that wing, and the right aileron goes down, increasing lift on that wing. This difference in lift causes the plane to roll to the left. So to make a turn, a pilot doesn't just use the rudder like you would in a boat. A smooth, coordinated turn requires a combination of all 3 controls. The pilot will roll the plane into a bank using the ailerons, and at the same time, they'll pull back slightly on the control column to use the elevators to keep the nose up, and apply a bit of rudder to keep the turn smooth and prevent the plane from skidding or slipping through the air. It's like rubbing your stomach and patting your head at the same time, but way more important. This system of control surfaces, elevators for pitch, rudder for yaw, and ailerons for roll, is the fundamental way pilots maneuver an aircraft. Modern planes have incredibly sophisticated fly-by-wire systems, where a computer interprets the pilot's inputs and sends electronic signals to actuators that move the surfaces. But the aerodynamic principles are exactly the same as they were on the Wright brothers' first flyer. It's a testament to a design that simply works. Long gone are the days of cockpits filled with hundreds of clunky, steam-powered analog dials. Today's flight decks look more like something out of a sci-fi movie, with large glowing glass screens. This is the world of avionics, which is essentially the electronic nervous system of the aircraft. These systems are responsible for flight control, navigation, communication, and monitoring the health of the entire airplane. And they have revolutionized air safety and efficiency. Let's start with navigation. How does a pilot know where they are and where they're going when they're flying over an ocean with no landmarks? They use a combination of systems. The Global Positioning System, or GPS, is a major one, just like in your car or phone, but far more precise and with multiple redundancies. This is often integrated into a flight management system, or FMS, which is a computer where pilots can program their entire flight plan from departure to arrival. The FMS then guides the aircraft along this pre-programmed path. Communication is another critical function of avionics. Pilots are in constant contact with air traffic control on the ground, as well as other aircraft. This is done through a variety of VHF and HF radios, but there's also a digital system called ACARS, which stands for Aircraft Communications Addressing and Reporting System. It allows the plane to send and receive short text-based messages, like getting weather updates or reporting its position automatically. The screens in front of the pilots are called the Primary Flight Display, or PFD, and the Navigation Display, or ND. The PFD shows the pilot all the critical flight information in one place: airspeed, altitude, vertical speed, and an attitude indicator, or artificial horizon, that shows the plane's orientation relative to the ground. The Navigation Display shows the programmed flight path, weather information, and the position of other nearby aircraft. It's an incredible amount of situational awareness all in one glance. And then there's the autopilot. The autopilot isn't just a simple hold this heading and altitude button anymore. Modern autopilot systems are incredibly sophisticated and are integrated with the flight management system. Pilots can engage the autopilot to fly the entire pre-programmed route, including climbs, descents, and even turns, with incredible precision. This doesn't mean the pilots are just sitting there. It frees them up from the manual task of flying to manage the overall journey, monitor systems, and handle any unexpected events. All of these systems, navigation, communication, flight data displays, and autopilot, work together to create a seamless and safe flying experience. The glass cockpit allows pilots to process a huge amount of information quickly and efficiently. It provides them with a clear picture of what the airplane is doing, where it's going, and what's happening in the environment around it, which is a massive leap forward in aviation safety and capability. When you're flying 7 miles above the ground, the last thing you want to worry about is something breaking. The good news is, airplanes are arguably the most over-engineered and safety-obsessed machines on the planet. Their ability to stay in the air safely is no accident. It's the result of deliberate design choices, focusing on stability, redundancy, and robust materials. Let's start with stability. An airplane is designed to want to fly straight and level. This is called positive stability. If a gust of wind rolls the plane to one side, the shape of the wings and the angle they are attached at, called dihedral, will naturally create forces that want to roll it back to level. If the nose pitches up, the design of the horizontal stabilizer at the tail will push it back down. The plane's natural tendency is to return to a stable state, making the pilot's job easier and, honestly, the ride smoother for passengers. The single most important safety philosophy in aviation is redundancy. What does that mean? It means for every critical system on an airplane, there is at least one, and often 2 or 3 backup systems. Planes have multiple hydraulic systems, multiple electrical systems, and multiple flight computers. A Boeing 777 has 2 engines, but it's designed to fly perfectly fine on just one. If one system fails, another one seamlessly takes over, often without the pilots even needing to do anything. This layered approach to safety ensures that a single point of failure can almost never lead to a catastrophe. Airplanes are also designed to withstand incredible forces and extreme weather. They are built to flex. If you look out the window during turbulence, you might be alarmed to see the wings flapping up and down. But they are designed to do that. This flexibility allows them to absorb the stress from gusts of wind, much like a skyscraper is designed to sway in an earthquake. The materials used, like advanced aluminum alloys and carbon fiber composites, are chosen for their incredible strength-to-weight ratio and their resistance to fatigue over thousands of flights. Before a new aircraft model is ever allowed to carry passengers, it undergoes a brutal testing process. Prototypes are pushed far beyond their normal operating limits. Wings are bent until they snap to find their breaking point, which is always far, far beyond any force they would ever experience in flight. They are tested in extreme heat and cold, struck by artificial lightning, and have birds fired into their engines at high speed. This rigorous testing ensures that the final design is tough, reliable, and ready for anything the skies can throw at it. Every single flight, whether it's a 30-minute hop or a 15-hour marathon, follows the same fundamental sequence of events. There are 6 main stages, and each one presents its own unique set of challenges and procedures. It all begins on the ground with the first stage, taxiing. After pushing back from the gate, the pilot uses a small amount of engine thrust and steers with a tiller or rudder pedals to navigate the maze of airport taxiways to the assigned runway. It's kind of like driving a very large, very expensive car. The second stage is the most power-intensive part of the flight takeoff. Once cleared by air traffic control, the pilots advance the thrust levers to full power. The engines roar to life, and the plane accelerates rapidly down the runway. The pilot monitors the airspeed, and at a calculated speed called V1, they make the decision to go. A few moments later, at the rotation speed or VR, the pilot gently pulls back on the control column, pitching the nose up and allowing the wings to generate enough lift to overcome weight. The plane leaves the ground. Stage 3 is the climb. After takeoff, the plane is in a steep ascent to reach its cruising altitude. The pilots will retract the landing gear and flaps to reduce drag and make the plane more aerodynamic. The engines are still at a high power setting, but not as high as takeoff power. The goal is to climb as efficiently as possible through the lower, denser parts of the atmosphere to get up to the thinner air where the plane flies best. This brings us to stage 4, the longest part of most flights' cruise. This is where the plane spends the vast majority of its time. The aircraft is at its cruising altitude, typically between 30,000 and 40,000 feet, where the air is thin, creating less drag. The autopilot is usually engaged, and the plane is in that state of equilibrium we talked about earlier. Lift equals weight, and thrust equals drag. The engines are throttled back to a fuel-efficient setting, and the plane just sails along its pre-programmed route. Eventually, it's time to come down. Stage 5 is the descent. Air traffic control will give the pilots instructions to begin descending towards their destination airport. The pilots reduce engine power, and the plane begins a gradual controlled glide downwards. They will often use speed brakes or spoilers on the wings to help slow down and manage the rate of descent. The goal is to arrive at the approach path for the runway at the correct altitude and speed. Finally, we have Stage 6 landing. This is the most demanding phase for the pilots. They configure the plane for landing by extending the flaps and slats to generate more lift at low speeds, and they lower the landing gear. The pilot takes manual control, carefully managing the plane's pitch, power, and alignment with the runway. After a gentle touchdown, they use reverse thrust from the engines, spoilers on the wings to dump lift, and powerful brakes in the wheels to slow the massive aircraft to a safe stop on the runway before taxiing to the gate. While airplanes are designed to be incredibly safe, in the extremely rare event that something does go wrong, there are a host of amazing safety systems designed to help pilots and to ensure we can learn from any incident. The most famous of these is the black box. Fun fact, it's not actually black. It's painted bright orange so it can be easily found in wreckage. And there isn't just one, there are 2. The first is the Cockpit Voice Recorder, or CVR. This device records all the sounds in the cockpit, the pilot's conversations, radio calls with air traffic control, and any audible alarms or strange noises from the aircraft. This provides investigators with a crucial audio timeline of the final moments of a flight. The second is the Flight Data Recorder, or FDR, which records hundreds of different parameters from the airplane's systems, things like airspeed, altitude, engine performance, and the position of the control surfaces. Together, the CVR and FDR provide an invaluable record of what happened and why. But many safety systems are proactive, designed to prevent accidents from ever happening. One of the most important is TCAS, the Traffic Collision Avoidance System. This system allows airplanes to communicate with each other electronically, independent of air traffic control. If TCAS detects that 2 aircraft are on a potential collision course, it will sound an alarm in the cockpit and issue a command to both pilots. It will tell one pilot, climb, climb, and the other, descend, descend, automatically coordinating an escape maneuver. It's a true lifesaver. Another key preventative system is the advanced weather radar found in the nose of the aircraft. This radar can detect storm cells, turbulence, and icing conditions hundreds of miles ahead of the plane. It displays this weather on the pilot's navigation screens, allowing them to see what's coming and plot a course around the worst of it. This is why you can have a surprisingly smooth flight even when there are thunderstorms in the area. Your pilot saw them coming long before you did. And what about emergencies on board, like a fire? Airplanes are equipped with sophisticated fire detection and suppression systems. There are smoke detectors in the cargo holds and lavatories, and if a fire is detected in an engine or the cargo bay, the pilots can remotely deploy a fire extinguishing agent, like Halon, to put it out, all from the safety of the cockpit. These systems, the black boxes for investigation, TCS for collision avoidance, weather radar for prevention, and fire suppression for emergencies, are the unsung heroes of aviation safety. They are the guardian angels working in the background on every single flight, creating multiple layers of protection that make flying one of the safest forms of transportation in the world. For all its marvels, aviation has a significant environmental footprint. The industry knows this, and a huge amount of research and innovation is focused on making flying more sustainable. One of the most exciting frontiers is the development of electric aircraft. While fully electric long-haul jets are still a long way off due to the limitations of battery technology, smaller, short-range electric planes are already flying and could soon revolutionize regional travel, making it quieter and emission-free. A more immediate solution is the use of sustainable aviation fuels, or SAFs. These are biofuels made from sources like used cooking oil, agricultural waste, or algae. The amazing thing about SAFs is that they are drop-in fuels, meaning they can be blended with traditional jet fuel and used in existing aircraft and engines without any modifications. This is a critical bridge technology that can significantly reduce the carbon footprint of flying right now. You may have noticed that most modern airplanes have those little fins that curve up at the end of their wings. Those are called winglets. They aren't just for looks, they are a brilliant aerodynamic innovation. They reduce the swirling vortices of air that form at the wingtips, which cuts down on drag. By reducing drag, winglets make the plane more fuel efficient, saving millions of gallons of fuel across the global fleet every year. It's a small change that makes a huge difference. The materials used to build planes are also changing. For decades, airplanes were made almost entirely of aluminum alloys. But newer planes like the Boeing 787 Dreamliner and the Airbus A350 are built with over 50% composite materials, primarily carbon fiber reinforced plastic. These materials are incredibly strong, but much lighter than metal. A lighter plane requires less thrust to fly, which means it burns less fuel and produces fewer emissions. Beyond the planes themselves, air traffic management is getting smarter. New systems use satellite-based tracking and advanced data analytics to plot more direct and efficient routes for aircraft. This means less time spent in holding patterns, more optimal climb and descent profiles, and ultimately, shorter flight times. Shorter flights mean less fuel burned, which is a win for the airlines, the passengers, and the environment. All of these innovations, electric propulsion, sustainable fuels, aerodynamic tweaks like winglets, lightweight composite materials, and smarter air traffic control, are pushing aviation towards a more sustainable future. The challenge is immense, but the spirit of ingenuity that got us into the air in the first place is now being harnessed to ensure we can keep flying responsibly for generations to come. So the next time you're buckled in your seat, waiting for takeoff, take a moment to appreciate the sheer complexity and brilliance of what's about to happen. That airplane is more than just a mode of transport. It's a testament to over a century of human curiosity, problem-solving, and relentless innovation. It's a flying symphony where the laws of physics are the music, and advanced technology and engineering are the instruments, all conducted by highly skilled pilots. From the four fundamental forces locked in a constant battle to the mind-boggling precision of a jet engine and the invisible safety net of avionics, every single component has been designed, tested, and perfected with one goal in mind: to make flight not only possible, but astonishingly safe. The fact that we can step onto these machines and be whisked across continents and oceans with a level of safety that rivals almost any other activity in our lives is nothing short of a modern miracle. Flying has connected our world in ways our ancestors could never have dreamed of. It has changed business, culture, and our very perception of the planet. And it's not done evolving. As we've seen, the next generation of aircraft promises to be smarter, quieter, and kinder to our environment. The story of flight is a story of human potential. A reminder that with enough ingenuity and determination, we can even conquer the sky. Thank you for watching.